why that's why we today we start with this new topic. As I said, what is not covered will be covered later on from what is left of torsional chapter, or the chapter in which we have studied torsion. Okay, so now today we talk about transverse shear. So we all know what shear is, what shear force is, right? We have studied shear force diagram, so we should know what shear force is, okay? Bending moment, we've studied about bending and bending stresses. Today's topic is about shear force and shear stresses, okay? Shear force and shear stresses. So how we calculate or how we estimate the shear stresses within a section and how the stresses are distributed within a section. So if we have like this cross section, okay, it's a rectangular cross section, and you have applied a force, okay, you have applied a force. So let's say that you have a cantilever. So an easier example, or the easiest example to represent this is you have a cantilever. You have a cantilever, okay, and you applied a force at its end. You applied a force, not necessary to be at its end. Okay, let me change it. You have applied a force uh, here. You have applied a force here. Okay, this is where you have applied a force, and you have the cantilever is fixed at this end, is fixed. So if we have the force is equal to P, sorry, I need to admit the student. Always they come late. If you have a force and the force is equal to P, okay, this is the force, okay, P. So you're gonna have a reaction. You're gonna have a reaction, and that reaction is R, which is equal to P in the opposite, okay? So all what we know that we will have shear forces in between, and if we draw the shear force diagram, sorry, let me use another way. If we draw the shear force diagram, so this would be the shear force diagram, okay? So you go up, okay, and straight all the way up to this point where the force is applied, then you go down, then you will have no shear at the rest of the member. You will have no shear. So this is the shear force that we will have. This is our V, right? So you have V from this point to this point. So that means we have shear stresses from this point to this point. How about this, what is left of the cantilever? Do you have any shear force or shear stresses? Is there any shear force or shear stresses? This is a question you could answer if you want to. Do we have any shear force? The shear force, this is the shear force diagram. So shear force diagram is to know where the shear is located. Okay. I also didn't tell you about torque diagram, axial force diagram. We also could construct those diagrams to identify the location within a member where the torque or where the axial load is at its highest value. Okay, so if, for example, this is our shear force diagram for the cantilever beam, we have shear force, right? So would it be, how to say, do we have any shear force beyond beyond the point at which the load is applied? Do we have any shear force? No. So there will be any shear stresses? No. Okay. So this is the shear force that we have within. So the shear force is constant. There's no critical. It didn't go up or down. So it's constant within this range. So if the shear force is constant, that means the value is V. This shear force, we have stresses due to the shear force. Okay, we have stresses due to the shear force. Or in another way, if you get the summation of these stresses, then you're gonna get a force equivalent to V due to these stresses. And these stresses are tau because they are parallel to the section. These stresses are tau because they are parallel to the section. Okay, so these are shear stresses. Now we know what shear force is and what shear stresses are and how the stresses are induced. Now we come to something else, just to know that even though that the shear force is transverse, but we still have something else called longitudinal shear stress. We have transverse shear stress. If you look at this cube, I'm going to explain to you how this longitudinal shear stress is developed due to the transverse shear stress. If you have this cube, and this cube is taken as an element from somewhere within the cross section, and we have the transverse, assume that the transverse is going downward, okay? Assume that the transverse is going downward, okay? So to establish equilibrium, the other opposite face of the cube should have a transverse shear that is opposite to this, opposite in the opposite direction to this transverse shear, okay? And then now we have other two faces. So I have now drawn this cubical or this unit of a cube, okay, or cubical unit, and then you have these two shear transverse shear stresses on both sides. How about these two other sides? In order for the cube to not rotate, to be in equilibrium, then I'm gonna have a longitudinal shear stress opposing to this transverse shear stress, and I will have a longitudinal shear stress opposing to the transverse shear stress, opposing to the transverse shear stress, so that we will not have so that the cube will not rotate. شيء بو تأخير هاتي.
دكتور والله كهرباء لا يهمك كهرباء
همو جار تأخير هي وداخل الدكة جاري كهرباء جاري خوتوبو جاري انترنت.
ناولا أستاذ همون لبر كهرباء لا يهمك كهرباء زور خرابة استاش كهربانية بلابتوب داخل نبويمة بموبايل داخل بويمة أو جا شحنة ما قرنا مولا دواتر
لهمو تلبكان most likely to أو مشكلة هي يعني كهرباء كهلايتو هي.
والله أستاذ جيم فرقة.
Okay. So now we have to establish equilibrium. We have, as I told you, on these two faces, I can establish the equilibrium on this side based on that this transverse force should be opposite to this, right? And on the other side, in order, because if you don't have longitudinal shear stress on these two faces, what will happen if I have this force is acting downward and this force is acting upward on this cube? What will happen? Shiar, what will happen if I have a force acting downward and a force acting upward, okay, on this cube? What will happen? Afnan, what will happen?
It's يعني it will stay in its place. They're gonna be يعني equal to each other.
No, if we have a cube in space and then we have applied a force on this face of the cube and this force opposite to this force on this face of the cube, so you can see what kind of forces you will have. This is upward and this is downward. Would they start to rotate? Is a couple of forces against each other. Would you think that there will be a kind of rotating force?
Yeah.
Yeah, so
Gonna
there will
rotate.
be, exactly. To stop the cube from rotating, what you gonna do? What you need to do? To apply what?
Apply a force.
A force, a couple. You could say a couple. Apply a couple of forces
Of
in
course. Yeah.
in the opposite or in the same direction.
The opposite direction.
Why you are saying as if you are asking me? Say it confident.
No. In the opposite direction. No, I'm sure.
In the
Opposite direction.
Okay, so if you look at these two forces on these two faces, are they in the opposite? Would they create a counteract to the moment that is created by these opposite forces? These two, the top and the bottom of the cube. I'm talking about the top and the bottom. This is where you have just now said I'm supposed to have a counter or a couple of forces counteracting the couple of these two forces. So that means we will have a force that should be, if this is clockwise, if this couple is giving a clockwise, the front and the back is giving, right? Am I right? Is giving a clockwise rotation, right? So the top and the bottom would give a counterclockwise, right? Okay. So that is how the transverse is developing longitudinal stresses along the longitudinal axis of the member. Okay. So if you understood this, we move to this example. We have a simply supported beam and is made up of three boards. Okay. And you have applied a load at midspan. In case of these three boards, okay, if I label it 1, 2, 3, 1, 2, 3, 1, okay, the second one is below, and 3, the last one. You could see those lines, right? So these are not, this is not a single board. You have 3 planks of wood, you could say. So the first one this, the second one is this, the third one is this, right? Okay, so now when I apply a force, if there is no friction in between the plank, as I said, if we consider that the transverse force is acting upward, okay, if the transverse force is acting upward, so based on this, this will be in the opposite, upward, okay, and this would be downward, okay, and this would be opposite to this. So because this would give a counterclockwise, so I need to have a clockwise. So clockwise would be this way, okay, okay. So let me see over here. If I apply this is upward, this should be downward. Okay, this should be, this would give me a counterclockwise. So this has to be clockwise and this has to be, sorry, let me draw it again. Hold on. If I have a force and this, if I take the shear force, this would be the shear force. This is the reaction. So if this is the reaction is equal P over 2, okay, the reaction, if I take a cross section over here, then the shear force would be equal downward, okay, downward. So the stress induced is downward, okay, the stress induced is downward. So on this side is downward. If I have a cube, okay, this is my cube, okay, okay, it looks like a rectangle. So the force is downward here, upward here, and this will induce longitudinal stress. The longitudinal should oppose it. So the up is, the down is like this. So what I'm gonna have, I will erase this because it's not clear. What I'm gonna have, I will have a force is like I'm gonna have a force longitudinally along the member, which goes outward, And on the other side, I will also have a longitudinal force which goes outward. This is the longitudinal stress. And if outward, it's supposed to be outward, and for any action, there will be a reaction. At the bottom, there will be an opposite to these forces. So that means I will have opposite to these forces. Okay. So in case an opposite to these forces. Okay. On the other surface of the plank. If we have these, this is the surface. Okay, this is the surface of the plank or that part of the wood. Okay. So if this is the surface, I will have a force that is going outward, and then on the same surface as a reaction, there will be an opposite longitudinal force to resist it from moving upward, from moving outward. Okay, to resist the plank from moving outward. But if the plank is not well bonded, what will happen? Okay, this is bonded together. This is unbonded, not bonded together. So what will happen? We look at the shape, if you could see the difference. Do you see at the end, the plank of the wood or the board has gone outward over here and outward over here? Do you see it? Do you see that the board has gone outward? Do you see the other one has gone also outward? Do you see the last one has also, I mean, of course, differentially has gone up outward because of the deformation at midspan for the upper side is less than the deformation of the board at the bottom side. That's why it has you have this differential extension of these three boards. Okay, so when you apply a force, you see the board is going outward if there was no friction between the board or the first board and the second board. There is no if there is no friction, that means there is no bond. That means the first board is not bonded to the second one, and the second one is not bonded to the third one. But if they are bonded, so you see they all have the same equal length. They have the same length. Okay, there will be no differential extension for the boards. There will be no differential extension for the board. Why do we have this differential extension of the board? Because of the longitudinal the stress of the first board is not resisted because there is lack of bond. That means not well connected, lack of bond. So it has slipped. Because of that stress, the first board slipped from the second, and the second slipped from the third. That's why you have these differential extension. Okay. So now we have two stresses. We have transverse and we have longitudinal. So at least we understand that when we have a shear force, we have two stresses. One is transverse and the other one is longitudinal. Now we deal with the transverse. Okay. So now we deal with the transverse only, and then afterwards, maybe tomorrow, we will talk about the longitudinal and how we calculate the longitudinal stresses. Okay, if you have a question up to this, if you have any question about the transverse longitudinal, you could ask. If not, we move to the formula on how we estimate or evaluate the shear force, sorry, the shear stress or the transverse shear stress. Okay. So we come, if we look at, is there any stress distribution? No, it's not shown. Not shown. Okay. So now we come to the evaluation of the shear. Okay, now we have the, Hakar, bochi takhirati. Now we have the shear force, the transverse, how we bale. Hakar bo takhirati. Tau is equal to V times Q over moment of inertia about the neutral axis times T. Okay. Okay, so now we have tau is equal VQ times moment of inertia about the neutral axis times T. So we need to know what V is, what Q is, what I is, what T is, okay? So if we look at tau, tau is the stress that is the stress. So if I show you the cross section, if we have any cross sections, is there any? Okay, so tau now, if we look at this cross section, you see those stresses. So if you want to evaluate the stresses at any, let's say at any section. So you could take this section. You could take this as a section from here to here and evaluate the stress or the tau at this section. Or you could consider your section is over here. Or you could consider your section is over here. Okay, and so on. And then afterwards, then again, if your section is over here or is over here. So as many as sections you'd like to have, as many as evaluation, you could evaluate your tau. So at this cross section, if you look at the shape of the distribution, you see tau is 0 at the extreme top and bottom side, and it goes this way, it goes up to the maximum. Maximum is located exactly at the neutral axis. So this would be the maximum of the stress of tau. So this tau over here is 0, just to show you the stress distribution. Tau is 0. Tau is max. Tau is max. Okay. This is due to shear force. Okay. Tau is max. And then it goes down up to 0 again. Okay, the same thing, the distribution is the same. So we have the estimation for the tau is all across the width is equal. Across the width is equal. Okay, so just across the depth is not equal. It changes from 0 up to maximum, then it goes down to 0. If I have the profile of the section, let me show you. If I draw the profile of a cross section and the shape, of course, it has to do with the shape as well. If the shape is rectangular like this one, so the stress distribution would look like this. The stress would look like this. I could say 0, 0, and the neutral axis, if this is the location of the neutral axis, then max here, then one curve and one curve to this side. So it's half a circle. Looks like a half a circle. So this is how stress is distributed. Tau. Tau distribution is, it has this form of distribution along the depth of the cross section, along the depth. Okay, but along the width is equal. Is equal. You have the same shape all the way from this side to this side. Okay, so this is the, where is the max? The max is at half of the depth, the max. Okay, so we need to know tau max is at half. That is in case if the shape is like this, is rectangular. Okay, if the shape is rectangular or square, because the neutral axis would be at the middle, at the mid depth. Okay, halfway from the top and halfway from the bottom. That's why tau max is at mid, and tau 0 at the extreme top and bottom side. Tau is equal to 0 at the extreme, equal to 0 at the extreme top and bottom side. So now we know the stress distribution. We come to the evaluation. Okay, we understood the stress distribution. We come to the evaluation. How can we evaluate? Okay, I think we need to solve an example to demonstrate how we can evaluate V, Q, and IT, okay? So I think the easiest example would be, ignore this circular shaft, okay? Ignore it, just we go to this rectangle, okay? So if I assume that I have V is equal to 5, okay, kilonewton. 5 is the shear force, okay? Too late. Not yet. I'm gonna ignore it. Okay, if I have the force is 5 kilonewton. Okay, if I have 5 kilonewton, it's the shear force. And B is assumed to be 300 millimeter. Okay, we have to give values. H, memorize it, 300 millimeter in case if we wanted to implement the equations. 300 millimeter square, sorry, millimeter. H is the depth is assumed to be 600, double of its width. Okay, 600. So you can easily memorize it. So because this is, I'm converting this question into a numerical question and then we solve it. Okay, 600, 305. Okay, memorized? Yes. Go to the solution so that we could apply the formula that we have just now learned. Okay, we come to the formula. Formula is tau is equal to V. Tau is equal tau, which means the stress, is equal to V times Q over I times T. Okay. Okay. V for this cross section is 5. So you don't need to think of V at all. All the time, V is 5. Okay. 5 kilonewton. If you want to convert it into Newton, so we make it times 10 to the power 3. Okay, because usually we come up with a stress that is in megapascal, and megapascal is Newton millimeter square. So all the rest we deal with millimeter, and the shear force would be in Newton, not kilonewton, converted into Newton, so it becomes 5,000 Newton. Okay, now we come to the easiest one. What is T? T is where you want to evaluate your stress. Would you want to evaluate your stress at which point? Okay, assume that you want to evaluate your stress at this section, this level. Okay, you want to have your tau at this level. Okay, at this level, from the top to here. Okay, this is where you want to evaluate. So that means this value. I want to evaluate this value. Okay, because my section is located here. My section is located here. Okay, this is my section. So what T would, what T is? T is equal to the width of the cross section at that section. Fortunately, the cross section it has the same T all the way from the top to the bottom. It doesn't change. It doesn't change. So T is in here is equal to B. T is equal to B. What is B? B is 300 millimeters square, right? 300 millimeters. We agreed that the B is 300 millimeters square. Okay, so that is B. What is H? H is the total depth. Okay, I don't need to talk about H right now. Just let me check what else do we have. T is equal to B. Yes. For this cross section, yes, is equal. Do we have moment of inertia? Yes. So can I calculate moment of inertia for such a cross section? Yes, it's so easy. Moment of inertia about the neutral axis for such a cross section is equal to what? What is the formula for moment of inertia about the neutral axis? What is it for such a cross section? What is it? S.
Gerbalin rectangular.
Yeah.
Master.
Yeah.
B square over 12.
B times
H cubical.
That's
a دوازة. باوري.
So
بس ما مثلا جو shape هي distort يعني rectangular إيش نيا بسوي أسابك هذا. مثلا أو inertia وش تشي يعني لامتحان أدري عند بيوم هموي بزاني شيوا بشيوا.
Sorry, I didn't focus on you because I received a message on this Zaim. I don't know what he's talking about. Anyway, so no, for regular shape, we have a formula for regular shape. Okay, so you have to follow the formula. For composite shape, we just deal with composite and regular shape. Regular shape is like a square or a rectangle. Okay, if the shape is square, then you use the same thing, b edge cube. At that time, b is equal to edge, so you cube whichever one over 12. If the shape is rectangular, then b edge cubed over 12. That's for regular shape. For circular, it has its own formula. For composite shape, I beam, T beam, whatever the shape is, composite of few rectangular and few other shapes like square or again rectangular and so forth. Then you come, based on what you have learned, you have to take the moment of inertia of each one of these shapes about its neutral axis and then transfer it to the neutral axis of the overall neutral axis of the shape that we will deal with later on. I'm going to show you, but that's all. You just memorize this formula. You don't need to understand how the derivation of the formula. Why is it used for what you said? What kind of shape is used for this one?
أو rectangular نيا ما مصا.
Yeah, this is rectangular. So we
Yeah.
use the edge
بس
cube.
سيارة كما ويا أجر لون من بس الشيوا regular كان دينيا أو دوسي داني عسانا. بس أجر شديد كجدي توا يعني وشي
No,
appendix
we
هذا
build,
يعني.
let me show you. Yahya. We have these shapes: square, rectangular, okay, and composite like T shape, okay, T shape. This is the most likely shapes that we will deal with, okay, this one, or an I shape, okay.